Right. So let's do a little bit recap. But Tuesday we were here, right? So we use call pattern this component to filter out those surfaces that are not very curved, right? So remember we set up the we have curvature, we turn it into absolute value, use its average to find the average of this curvature. Just try to calculate the average value here, and then we use this larger than to set up the filter that if you are larger, I would further divide it into 3 by 3, or if you are not very curved, the curvature is lower than the average, I would just keep it as it is, right? So we use this call pattern. So we would put this large and then, so we compare all this curvature and the average. So this curvature, all the curvature of all the surfaces, and compare the curvature with the average curvature. If you are larger, and we will have this table, right? This list that if you are larger, that will be true. If you are smaller, that will be false, right? Smaller or equal. So true, if you are larger than the curvature of this subsurface, if it's larger than the threshold we set up, that'll be true. So this is a pattern that true, true, false, 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 something like that. This is a pattern. So, and we input this pattern into this component. It's called call pattern, right? Call pattern is a component that give me the pattern, true or false, this kind of pattern. If you are true, so the first item is true, then first item I would just let you go. But if you are false, the second item is false, and then the false would not, we will block it. So you won't see that after this thing. So this is you can see how many curvature, how many subsurfaces that have the larger surface curvature, right? So this one is like we have 226 surfaces in total that they have larger curvature. Before that, we can see how many surfaces we have. So in total, it's an isotrim, right? From this isotrim, in total there are 625 surfaces, right? So that means only 200 something surfaces that are very curved, right? So that's how we use this call pattern. So it's like a filter, right? So give me the list of true and false, and I'll just filter out those false one, right? So this is the one that we filter out, right? We kept. So this is you are very curved. So for these subsurfaces, I want to divide it again, right? Because it's a little bit like a fabrication process. If you are very curved, it's hard to make. But if you divide it again to a small surfaces, maybe we can just use a flat surface to do that, right? So that is one of the applications that we can use, right? So these subsurfaces are very curved, and then would rebuild it again, right? Just like before, we rebuild the surface, we reparameterize it, we use the same domain method and use isotrim just to subdivide it again. This part is exactly equal to the same as this part we did before. We have bigger surfaces, right? But we subdivide it. The only difference is here, when we put these subdivises into the further subdivision, here is one thing we have to be aware of. This is a graphed input, right? So this is a graphed input. Before, in the previous one, that when we are using these to subdivide the surface, we only have one big surface, right? So I only divide that one. However, if we want to divide many surfaces, we need to graph it. So that means, okay, this surface, you are in your own room, and you will be divided into 3 by 3. All right. Otherwise, that will be the wrong data structure. So be aware of this thing, right? So do you all have this subdivision? Okay. So if you are okay, and this is already subdivided even more, right? 3 by 3. So for one unit is further divided into 3 by 3, all right? So we use this to control. You can change it to 5 by 5, like this one. There's more detail. right, like these. And if you, so that I just go back to the 3x3, right? Right. So those are the very curved subsurfaces, and we just further divide it, right? And what about those surfaces that are not very curved? So we still need to keep it. If we just use this one, then we only have this part, right? So we need to keep those subsurfaces that are not divided as well. So we use another call pattern, right? We use another call pattern. We put the entire subsurfaces into this call pattern again, and we use the same list, true and false list from the larger than. However, here we need to invert. So like invert is straightforward. If you are true, you become false. If you're false, you become true. So just, compensate this whole list. So right click here, you can see the invert. So please remember to check out this one and put the isotrim, the output from the isotrim here, the entire subsurfaces into this thing, into this call pattern. So you can see these are the subsurfaces that are relatively flat, right? So it doesn't have to, they don't have to be subdivided again, right? So these subsurfaces and also the further divided one, they are, combine these two, they are the subsurfaces in total we have. And the next step is, remember that the challenge we just said, we said in Tuesday, see if we can put the color code again on these subsurfaces, right? So that's what we are going to do today, right? So these and that. So you can see these subsurfaces are further divided, and this is not divided, all right? So we use the same thing here that use this gradient component to do all of the color coding, right? So that will be exactly the same thing that we need to calculate the curvature again and put them together and use this curvature to do the color coding, right? So first of all, I want to merge these two things. So this one set of surfaces and this is another set of surfaces. So now I just want to use merge. So please follow me. Merge. Let's use this component. Just put them together just like one list, right? So this is a one, this is another one, all right? Be careful, here is a grafted, right? This is grafted. You can see the wire representation. This visualization is a grafted. We don't need a graph structure here. So please, on the surface output, this isotrim, we further divided them, right? One room has 9 surfaces now, right? So we put every subsurfaces into individual rooms. And so, okay, you have to be divided into 3x3, this divided 3x3, and we have so many subsurfaces again. But we don't need a structure anymore, so we need to flatten the output here so that they can be flattened, the structure can be removed, and they are all in the same lobby. All right, so that's what we need to do before we do the merge. All right. So in total, how many subsurfaces we have? So including those bigger one and smaller one, we have 398. It looks a little bit weird because it should be more, right? So we need to flatten here again. The output to the merge, we need to flatten it again. So that will be 2,433 subsurfaces here. Oh, what's going on with my? Give me 1 second. All right. Okay. So we merge them together. We flatten the output of the merge again. So make sure that every subsurfaces now are in the same room, right? And the rest of the part is Just like we did before, we calculate curvature. Remember how we calculate curvature? We need to use area to calculate the centroid of each subsurfaces, right? So we have so many points now. You can see that even the smaller one has its own centroid, right? And we talked about this before, that the centroid is geometric center, so it's not on the surface, right? So we need one more component called surface closest point, right? Here. Before we go too far, I'm going to lower this to 2 by 2 just to prove the concept, not crash my system. Alright, so I want to reduce the number of subsurface. Now everyone just divided to 2 by 2. 3 by 3 might still too heavy for my computer. So we have the centroid, but we need to put this centroid on the surface because we need to calculate the curvature. Alright, so this centroid is the point, and these subsurfaces are in the subsurface here, they're in the surface. I'm going to turn off the preview of the area because these are the points on the surface, all right? Remember, we use this component because sometimes the surface is like a bowl shape, and the centroid, this component calculate the center is a geometric center, so it will be floating, it won't be on the surface. So it'll be like it's somewhere here, like this, right? But because we need to calculate the curvature, we need a point on the surface so that component can work. So we need to use this component, surface closest point, to move these points to the surface itself. And then that point will be on the surface, and that can be calculated for the curvature. All right? So exactly the same thing, I will just do it again. All right? So this is the next component is surface curvature. This one, like swollen, this one. Just like you got bitten by the mosquito. All right. So let me put a scribble. Just remind us that the second time subdivided surfaces. These. So just remind us. And I'm going to put this thing back to this isotrim. Just another scribble that the first time subdivided surfaces. Right? Just not confuse ourselves. All right? Okay, so just like the thing we did before, we put the surface here into the surface curvature calculator. Remember, we need to use UV point here, not a point. So this point is we talk about this on Tuesday. This point, the output of this point is like an absolute XYZ coordinates. But UV point is like a local coordinate system, right? So this UV point, we use this thing to calculate the curvature. And we are using the mean, the average curvature, to do the visualization. So the next thing is, I will just do a little faster here because we need just the same thing that we done on Tuesday. We need to calculate what is the biggest curvature and the lowest curvature, right? We need a boundary. We have so many curvature here again. I didn't know which one is the biggest one and which one is the lowest one, so that we can put it into gradient component to do the visualization, right? So we sort the list. After we sort the list, we can see the smallest one will be on the top, the biggest one will be on the in the last, right here. So we just do it again, like list item to grab the first one, right? The 0, 1 is the smallest one. So this is a lower boundary of the curvature. The other one, list item, is, remember how we get the last one? We use list length, right? Calculate how many items here, and use this as an index, but here is expression x minus 1 because the index is always minus 1. And this one go to list like that. Okay, so this is the lower boundary, this is a higher boundary. And we use gradient again. So gradient, find this component, right? I'm going to change my preset to this one. So there's a lower limit and upper limit again. And the parameter is all the curvature you calculated, right? So that is here. Before you sort. If you put a sort into the, if you use this sorted list, you'll be a problem. So make sure that you are using the mean from this surface curvature here directly. Go to parameters like this one. So here you can see all the curvatures are mapped to an RGB code, right? And let's use custom preview. This one, the window with a green sphere. We use this component to visualize the materiality, right? And the geometry is all the subsurface here, this one. So I just put it here into the geometry. And the material is the cutter. All right. And I'm going to turn off all the preview before. So we have further visualization of the cutters. All right. I'll stop here. Let me see if let me know if you have the cutter here. The one more subdivision cutter. These are already done before, right? We just use the same thing. If you miss this part, you can go back to see your code. We calculate the curvature, right? And we use a curvature. We map these curvatures to the color code, right? And how do we calculate the curvature? We use a point on the surface, right? It needs a surface and a point on the surface to calculate the curvature. So we use the area to calculate the point first, and we use the surface closest point to move that geometric center to the surface, on the surface, right? And then we use the calculator for the surface curvature to calculate the curvature, and then we put this curvature into the gradient. Before we put it in, we need to calculate what is your biggest curvature and the lowest curvature, because we need, just like the Celsius or Fahrenheit, right? Remember that I need to know 0 degree and 100 degree as a boundary to map the cutter from the lowest one to the biggest one, right? The lowest curvature is what, and the biggest curvature is what. I need these two boundaries so that I can map the entire range of the curvatures into color code, right? So that we have the RGB color code, right? So the red one specifies that you have large curvature, and the green one specifies that you have a lower curvature. So you can see this part is very bended, right? It's very curved. Here, the curvature is large still here, but it's less than the last time that when you subdivide it. You can go back to change the subdivision. I'm going to change it 3 by 3. So you can see this subsurface is divided into 3 by 3, right? So here are less high degree curvature, right? All right. So far, so good. Okay. You all have this thing. Okay. Let me see.
This is red. I don't know what.
That's red. Okay. Let me see. Data conversion failed to geometry. Okay, so this is here, this here, because yeah, so that is to calculate the index for the last item, right? And we need to grab the last item from here, and this should be the lower one. This the parameter is from the mean. Okay, that's good. And this is another geometry should be from here, right? Geometry, so that should be surfaces. There we go. See? Yeah, you got it. Yep. 1 second.
For whatever reason, this is like flipped.
Flipped?
Yeah.
Oh, that means that you might have the lower curvature and curvature revert. Upper one, you might put a sorted one. Parameter is from the mean, that should be fine. Negative. Okay, so that means you miss. Oh, sorry, I missed one thing. Yeah. Yeah. Sorry, I did. All right, I missed one component that I would. I forgot to use absolute.
I'm just missing like the first two that you use.
First two.
Like the first two, like how it connects to the rest.
Oh, okay. So where's your subdivided here?
Also, when I tried to download Rebuild Surface, it like wouldn't download.
Oh, do you have the lunchbox?
That's what I meant. The lunchbox.
Okay, you need to use lunchbox. So why don't you shift to this one, save the file, email this thing to your,
Okay.
and download, use the desktop. You're all good? Okay. I missed one component that after the curvature, I need to use the absolute to get the absolute value. Sorry about that. So here should be an absolute. That when we calculate the curvature, we put it in to get the absolute value, right? I forgot this one, sorry. So this one is here. Otherwise, we will have the negative one. So this is this. We sort the list after the absolute, and then use this list item to grab the first one and last one as a lower boundary and a higher boundary, upper boundary, and put it into gradient. So I put it here, look more clear. Sorry. Okay, so this is the result that if you further divided it, the subsurfaces and then you visualize it again. You can change the color set if you want that. If you are not happy with the color set, that green one or something else, all right, up to you. Rainbow one, ugh. All right. It's okay. Not that bad. Black and white. Oh, okay. This one looks better. If you want to revert the color, that for example, this one is a very curved one, but typically we use the red one to specify this harder one, right? So if you want to revert this color, one way I would do is to just because that means the high value is blue and low value is red, right? So in this sense, if I want to revert it, I won't touch this gradient. I will just swap these two. The lower boundary become upper boundary, and the upper boundary become lower boundary. Yeah, I just like revert the scale, right? Revert the scale. That's something that you can play with. Okay. So far, so good. All right, let's move on. There's one more thing to do only. So now I'm going to disable this one. Let me disable here. So we have this thing, right? We have this thing, and now I want to disable. I just don't want to get into this heavy calculation because I'm not going to use this now. I'm going to disable this ISO trim and also this call pattern is larger than. All right. So just disable this one and this one so that make sure that it doesn't calculate anything now because I want to go back because the next one is to do more tiling. All right. I'm going to turn off the preview, turn on the preview of the first subdivided surface that we did, very first one. All right. So let's use this one to do more tiling. Okay. So this is for data visualization. This one, we can move it somewhere else. Okay. Now I'm going back to this, the first time we subdivided the surface without, yes? Oh, I just don't want it to be calculated because it causes a lot of performance. So on this sense,
That one.
and also I turn off the larger than larger. Yeah, turn off this one, disable it, and then you won't have calculation. Yeah. Another reminder for you is that when you want to change any parameters, that for example, when I changed the subdivision from 3 to 2, right, or 2 to 3, I won't drag the slider. It's very bad if you drag the slider, like the number slider, like this one, like this. If I want to change the number, I won't drag it to like a 25 to 30, because when you drag the slider, it will calculate all the numbers you pass through. Like 25, 36, 30, you calculate everything like this one. So I will just double click, enter the number I want, and hit enter, so it will calculate that number only. Anand? Okay, let me see. So the curvature, so it has problem here. So you miss a parameter, so it should be from this one. Yeah, there you go. Okay. And then you're good? Okay. All right. So just a reminder, or sometimes I will disable the component before I make any change, right? So I don't have to let the whole system calculate all the numbers that you will probably need 30 minutes to wait for it. I'll come back. So that is a bad thing. Don't drag the slider, just enter the number directly, right? Okay, so come back here. Now let's make a small tile. Okay, very simple thing, very simple tile. Let's go back to Rhino. All right, I'm going back to the top view. I may just try to make something really simple. I'll use rectangle, create a square like this one, all right, square. It doesn't matter how big it is. I just make a square. Let me move it to here. Anywhere on your canvas is okay. And I'm going to offset it. So like I use distance 1, so like this one, or offset out is okay. So just like a 2 concentric square, like this one. All right. I'm going back to the perspective view, find these 2 squares. I just use rectangle tool, so rectangle here, rectangle in the Rhino, and hold the shift to make it square, and use offset command offset, this one. And if you want to change the distance, here's a option. You can change that. The offset distance, if you're 2, that'll be thicker. If you change it to 5, that'll be even bigger. So offset. I just use 1 here. So you click it, enter the number you want, and you have this offset. Right? All the others, I never use it, so I just do this thing. Right? So you have two curves on the floor, one small square, one bigger square. Right? And please select both of them and type extrude curve. In Rhino, it's not in Grasshopper. So I'm going to make a motif in Rhino, and I'm going to associate this motif, this tile, into Grasshopper. And we will map this motif to the surface, right? So the extrude curve, right? Let me change to the shaded view. Okay, when you extrude curve, you can start to see how big you want to extrude, how tall you want to extrude. But be careful, here is something that I would suggest. Here's an option called solid. All right, solid. So if there's a solid, should be yes. So when you extrude it, you look at it is a whole solid thing. Let me do it again. If you have the solid set no, and the extrusion will be just like a hollow thing like this, right? So that means it has a very sweet function that when you extrude, you can select if you want to cap it or no, right? So I would suggest let's cap it, like this one. So that this. So I'm just making a tile, right? Like this. Very simple thing, right? It doesn't matter how big it is or where it is, all right? So just make this geometry. And let's go back to the Grasshopper. I'm going to associate this geometry into the Grasshopper. So let's use geometry, this component, right? The hexagon one. And then we want to set one geometry, select this one, right? You can change the component's name so that you can remember what it is. So here you can hover over on the component, you change the name. I say this is a tile 1, something like that. Okay, so the tile 1. Or you can give it a name like a frame tile. All right, like a frame. Like this one, frame tile. All right. Okay. The next thing we want to do is to map this tile to every subsurfaces, and it should deform with that. Okay, it sounds very complicated, but it's actually very easy to do. All right, just follow me. First of all, we need to use a component called bounding box. So this is a bounding box. All right, it looks like a cheese. This is one. All right. So just directly put this frame tile into this bounding box, and you will give you the entire range. This is the box to the smallest box that can contain everything, right? So there's a bounding box. Okay. The reason why we use this bounding box is bounding box will become the pilot for us, right? So I don't care what kind of geometry, what kind of shape your tile is, but as long as you have a bounding box, I'm using this box to map to another box. So that means we need to create a lot of small boxes on the isotrim surfaces as well. So like the subsurfaces. So let's use this component called surfaces box. Surface box. Surface box. All right. So surface box requires 3 inputs: surface, domain, and height. For our application, let's put the surface, the isotrim surface into the surface. The same go to the domain. So this put this twice. So it's still from the surface. That means I don't need to calculate other domains. So if you are that big, you are that big. All right. So I don't need to have another domain to map it. Anyhow, it's just like we just put these inputs twice. Right. So they are both from the isotrim surface here. Once you put it, you can see it has a box already. Let me hide the preview. You can see it's a wireframe. You already see the box. Every subsurface has a box now. And now the height is how deep your box should be. So that's use a slider. I use the 0.1 to 10 to 5. Right? Put the height. Right? So when you put the 0.1, you can see there's a thinner box. If you change it to 0.5, you see the box is a little bit thicker. All right? So it should be straightforward. So that means we have this box and we have that box. Right? So this box, surface box, is just like a bounding box again, but it's just for the surface. So basically, it grabbed the surface into it and try to extrude a box for you, right? So that is what it did, what it does, right? So anyway, so we use the surface box to make a lot of boxes on the subsurfaces, and use bounding box to make the box for this tile. So that's the last thing we need to do is to map this box to that box and carry the tile according to how you deform your box. I deform the tile as well. Okay, so that's another component. We call it here box morph. Sorry, box morph. All right, it looks like a orange box and smoke gray box. Box morph. Right. So you can see it has 3 inputs. One is geometry. So the idea is that I have a box, all right? You have a box there. I'm going to morph or deform this box to that box. Okay, so just like you squeeze this box into that box and carry the geometry in the box to do the same morphing, all right? So the reference is from your bounding box, all right? And the target is from this the surface box, all right? So where you go, right? This is you are right now, and you want to morph to there. So that's the target. Geometry is the things that you want to carry to. So that's from the frame tile. Go to here. All right. And I'm going to disable all the preview from the path. After that, you should see these geometry like this. It's very easy. Let me bake it, and you will see more detail. Now the tile is mapped to the surface. Right. And that's just a very simple frame, right? Frame-like tile. Okay. Nothing else, just 3 more components. Okay, let me enlarge it. Can you all see this thing? Can you see the design? Yeah, it's good. It's fun. You can design your own tile.
When I baked it, it didn't put the holes in it.
Oh, really? Let me see. Yeah, there you go. That's okay. Sometimes it's just funky. You good?
Yeah. Is there a way to put line weight onto
Mm-hmm.
like this like a Arctic or I was curious, like visualization. Is there a way to look at like line weight so you can see the definition a little bit better?
Oh, you want to see the outline?
Yeah.
Okay, so yeah, I will talk about this thing. You all good? It should be straightforward. It's just like 3 more components and do very complex things. Okay. So, what's your name? Sorry. Hunter. Okay. Hunter just asked that when we change to the Arctic view. Sometimes, for example, I have the frame, like the wire frame outside. Like you can visualize the frame. There's an option for you to change the rendering. So here, if you want to change the rendering, you can go to the tools here, the tools option, and you have this window pop up, and go to view here. The left part, the view, you can pull down. Here's a display mode. So display mode is like how you want to visualize your design or render your design. The wireframe, shaded, rendered. If you make change before, that'll be red, blue color. That means you make change. It's not default setting. So for my own setting, I made some change here. So if you want to do something, you can go to Arctic, like the wireframe one. Click this here, and you might see some options here, like you want to show the ISO curve, you want to show the tangent edge, you want to show something here, or you can even go further. You pull down the menu again, and here's an object. Pull down again, and the surface. I put this edge thickness just 1. You can turn it to 0, and that won't be a line. Okay, so it can be very detailed, because right now it's more like an engineering software that it open a lot of options for you. So you can very detailedly control how you want to visualize different kinds of geometry. All right. You can also go to the like a global setting here. Show ISO curve. You will see the ISO curve like this. But ISO curve is not a frame. Okay. ISO curve is the curves we describe the surface. So it looks a little bit weird here, right? And so you can check out to see what kind of setting you want. Basically, my setting is like this. If I don't want to see the seam, I just uncheck these things. I go to surfaces. I put the edge width thickness here. 1 or 2. You can be very thick, but it looks really bad. I just use 1 to highlight it. If you want to visualize the curves here, you can do something else, right? Just click OK. You have your setting like this. Same as rendering, you can change the rendering a lot, right? All right. Thank you, Hunter. All right. So now is playful time that you can design your own tile. And please do it now. Do it now. Please design your own tile and morph it again. And let me see if you can create another tile and morph it. All right. So let's do it now. Let's just use 5 minutes to do it. So design your own tile right now and put it into this component. Everything will be fine. Okay, I can show some example. So that's what I did. What we did for the first one, right? It's a very simple frame, and I did something very weird. Remember the Aaron Howard, the beautiful tiling. Try to design something like that. It'll be nice. That I have to admit that I'm not very good designer from this aspect. That I think it doesn't look very well. But sometimes you can design even more aggressive. Yes.
What was the settings after you draw your shape?
What?
After you draw your shape, what was the next step?
Let me see. Okay. So, offset.
Offset.
Yeah, offset. Okay. So that is for this exercise. You have more space to create your own design. So for the deliverables, at least you have to design 4 tiles. 1, 2, 3, 4. 4 tiles. All right? It can be very ugly, but one suggestion is when we design a tile, make sure that can reflect like a materiality that when they can connect together. Right? They can connect. So for example, when I design this tile, they can be connected in this way, right? So this is a tile look like this. And when they put them together, it creates a circle or something like that. Right? So make sure that you can connect to each other very well. All right. And please use Octave view, just like a previous assignment. Use Octave view to output all your images and put it into the PDF, right? So 4 tiles, at least 1, 2, 3, 4. And then 4 tiles that will be applied on 4 different surfaces, right? So I just use, so this one is mostly like what we are doing here right now. I use the ellipse to create a surface, right? You can just change the underlying, the driver geometry to get different surfaces. For example, this one I use it like a beam curve to do something like that. All right. You don't have to use this system to create a surface, but at least the surface needs some curvature that you create. All right. I would highly suggest you just stick to this system. But if you have your own system to create very beautiful surface, by all means, right? But just like if you don't have any idea to how to create a complex surface, you can stick to this system. Just change the profile, right? All right. So 4 different surfaces. Each one has 4 different tiles, right? So 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. All right. So for example, this one is ellipse. The base is ellipse. I just make this surface. There's tile 1. There's tile 2. There's tile 3. There's tile 4. Right. Sometimes I change the density. All right. But I would suggest you, if you are using the same design like this, 1 column, just stick to 1 density. All right. You can have more different. I don't mind, but just like try to keep it a consistency. And here's a challenge to you. Did you recognize this? That how many tiles we use here? And that's not only 1 tile. We have 2 tiles. And again, this is very bad design, so forgive me. So this shape and this shape, I use 2 tiles to make this tiling pattern. But so far we just use 1 tile, right? Just use 1 tile is fine. But there's a challenge for you. Think about how to use 2 or even 3 different tiles on this to create a kind of pattern. So you don't have to stick to 1 design, 1 pattern. You can change that. So that is altering like a one even line. Even column is this tile, and odd columns are another tile. All right. I will post the script later, right, of this one, how to do this thing, right? But think about this. It's a challenge for you. If you, this is like a bonus. If you don't just follow the same structures, you are fine, right? It's not straightforward, but I would suggest you challenge yourself. Right. Right? Does anyone have new design already? All right, let me see. Whoa, very complicated.
Yeah.
Like a car.
I need to have a second layer probably to be the surface because they're
connecting. That's awesome. Yeah, I would suggest that, for example, this one, zooming, it's like you are connected with a point, right? Mm-hmm. So on the fabrication perspective, it's almost like hard to make it work. So think about this thing, that how you connect to others. right? Yeah, it's very complicated design. Yeah, same suggestion I will give you. Can you zoom in a little bit? So they are connected in this way. That might not reflect the materiality and tectonics. So think about this thing. Yes,
I mainly work on Mac, and the Lunchbox plugin doesn't work on Mac. Is there any?
it doesn't work on Mac. I
Yeah.
think so.
It said only Windows, and when I tried to download it, then there's.
Oh, it's not for the window. Yeah, it's not for the re. Okay, let me see. Which one is cancel?
Um.
Okay.
Sorry, everything is from German.
Lunchbox. All right. Do you mind shift to this desktop? Just email your work to here. Otherwise, if you don't have Lunchbox, that'll be very bad for this one. Okay. Unless you have design.
Uh, so for this one, I did a cylinder, but it spewed out this when I baked it. And then for this one, I did a hexagon. And it did the same thing.
Okay, you might bake it the
Like
wrong
it
one.
shows it on here, but
Yeah, sometimes the rendering is problematic. Let's try again. Yeah, there you go.
what is it?
No, it's just like sometimes you have the it's just a lock, which make sure you are lucky you did. It's not very promising, especially you have so many surfaces. So the calculation fail, you will just go
How do
back.
I get like shapes that do this? Like stick out like that.
Oh, you have to have your imagination. Think about this thing. Think about this thing. All right. Oh, that's your homework.
Use like just more like tools and stuff.
You could, but suggestion here is that you see this point to point.
Yeah.
So, from the perspective of tectonic, it's hard to make it, right?
Right.
So I would suggest you think about the tile connect, how they connect to other people.
So when I'm going to make a shape, I have to make it as it's connecting, or
I would suggest, right? So that, for example, that when you put a tile together, we want to fabricate it, and if we have this kind of design, it's hard to fabricate, right? It's hard to fabricate. You good?
yeah.
Okay. Can I find? Okay. No problem. Yeah. All right. So we already done this exercise, this workshop. It's short, but it is very useful. That morph tiling is like something that you can really quickly get very complex design and try. I would highly encourage you, if you make one thing that is, try to print it out. 3D print it. We have two big 3D printers this year, and try to see how it look like, like what it is, and feel this kind of thing that when you see a physical design, that'll be very rewarding, right? Okay. Let me see if I have other example for you. Okay. So like this project is morph tiling as well, but in the end, I don't like the morph tiling. This, just like I said, this is not very architectural, because you see the motif, it looks like this. It's actually really hard to make. So it's like a uh, lack of the tectonics here. But still, you can see that how the space is created here. That's one of past example. It's not. There's another thing that I did in when I was a student. You can be done in morph tiling as well, but this will be more complex system behind that. All right. Remember I show you before about this emerging object, this one. I really like their work. They're very straightforward, beautiful. I want to highlight this one. You see, it has this is the same tile. This is the same tile. Think about how if you can do this thing. It's the same tile. When you morph it, it just rotate. Sometimes it's here, sometimes it's there, sometimes it's this, sometimes that. Same tile, but just keep rotating it. So think about this: when you morph it, can you apply a system that every time I morph it, I randomly rotate it 90 degree or 45 or 180 degree. So like a here, 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 and there. So just even one tile, you can create a lot of different pattern. Just keep rotating it. Uh, because the interface, that's why I'm always emphasize this interface with other tiles, they are designed, right? So always like these things are connected. So no matter how you rotate it, 90 degree, 180 to 70 degree, you can always perfectly fit with other tiles. So that's a detail of this work. So there's another thing you might want to try is that when you morph it, see if you can every time just morph differently, right? So that's another thing. This is a great work. This is a very um, interesting work. Then I like the detail here. You probably cannot see it, but behind on the back here, they they were using the clips that the stationary that you can get from the stapler, that staple that is like a long leg clips to fabricate it. I think it's fragile, but it's fun to see that. Um, there are a lot of applications to do that. This one is another one, but it's a more complicated tiling. Another one is where is it? Where is it? Here. I showed Noise Architect's work before. A very good reference. You're going to see that once you know how to do morph tiling and the attractive point and geometry representation, and also like a attractive point and the how to represent a surface into lines, points, and solid. And you look at these projects again, you say, "Oh, I can do it." So let me show you one thing that's very straightforward. Like this, right? It definitely can be done in the morph tiling. You don't even need to morph anything. You just frame wireframe only, right? This is one that you might morph something. It's more like paneling, but this one definitely is like a morph tiling work, right? So you can see the unit here. You just put this unit. So to try to decode how it is mapped, right? Some other things like there's an attractive point. We talked about this before. This is another morph tiling as well. Now this one, right? A lot of work, as long as it's about facade, you probably can apply these techniques. Now this one, attractor points together. This one definitely morphing, right? Just wireframe, straightforward. Formation, another good studio. I like this project that Tristan Alahade was my colleague before, and he has some humor on his work. That this is actually generated from the Great software as well, but he only has 3 or 4 tabs because it's casting, so it cannot make too much mode, the foam work. But this one is like you can already feel that you can do this thing with your script, right? It's just changing the things, and that is interesting work. But this one looks complicated, but behind that is exactly the same script that we use. Right? But the good thing, the creative part of this project is they are balloons. They are balloons, right? So that is brick, just do the morphing, right? Again, the same thing. Fabricated. This is another morphing tiling. Exactly the same thing, right? It's just like very complex tile. This is not even go to morph, even easier. This one is another one you can think about, right? A lot. So there's so many things that you can implement with morph tiling. This is another one. Good work. It's a little bit beyond morph tiling. This is my classmate. But you look at this, you still can somehow decompose this very complex shape into units and to simulate in with the morph tiling work. That this one. This work is a lot of portion efforts are on the fabrication, the materiality. This work. There's another one. Maybe not a good example. That this is another one. This is more like a discrete morphing. Discrete. A very similar idea. That's fine if we have the last one. This is an artist I like very much. His work is amazing. This is directly application of morph tiling, right? It's just like the Unix aggressive like this, but geometry exactly the same thing. Beautiful work, beautiful work. John Gray, his name John Gray. That he has a lot of beautiful work. This is like a light lamp, like the paper lamp, as a installation in the museum. He has there's another morph tiling again, exactly the same thing. Play this idea again and again, right? There's different materials, different scale. If you have really complex geometry, like this one, the same thing. It's just like a very complex geometry, the shapes, the surface. So once you figure out a very complex surface, you just apply the skill again. Beautiful work. Amazing. His work has a lot of these kind of features. You can tell that, right? It's like this is a tile, you just put the tiles together. There's another one, direct application. John Gray. Highly recommend you take a look at his work. There's another one. And I was when I saw this work, I was interested. Oh, this guy is good. And then just check it out. I think from his work, I say this gentleman must have architecture degree. And yes, I was right. It's from architecture. He did some architecture work before, a long time ago. I shifted to artist. Yeah, very nice work. Yeah, this one, this. Nothing new. It's just like how you create this complex surface and just fabricate it. And fabrication is from the morph tiling again. All of his works are like this. Like this again. But he put a lot of efforts on the fabrication of materials, right? But this is another morph tiling. Yeah, very beautiful work. And this one, right? Like this. This is really hard to make. That is done in CNC router, but this is almost like a double-sided CNC router, and this is a very complicated process to make this with wood. All right. Any question? Who is this? Oh, it's a bad design. This is another artist I like very much. Zimmer Pellet. It's the same thing, morph tiling. But she is an artist that focuses on ceramic design, and all these things are ceramic, handmade, handmade. But she's insane that she set up competition rules for herself. That I just do this. I follow the rules only. I don't do anything else. She handmade these things. But behind that is you can see this is an almost tiling style. This thing, it's just like she did this with hands, but exactly. Let me see the work I really like this one here. It's just surface extrusion, but you can see this is a tiles, and that's ceramic. It's just like she's really crazy artist. Yeah, she has a lot of work. This one is so weird. Yeah, powerful work, very powerful. Like this. Yeah, this is a ceramic one. This is just pattern. Yeah. Anyway, explore more. Okay, so the due of this assignment is Tuesday, okay, 9 a.m. before the class. Submit your work. I will open the assignment later. So please submit the work. I think this one is relatively simpler. So just design your own tile and 4 different surfaces. All right. So you can check. You can see these documents on the canvas as well. So you can for your reference. Right. So these works are inspired by these artists from the ceramic one that try to do this kind of like octopus feet things, right? So just create some works here. Arctic view, all right? Isometric view, Arctic rendering. For this thing, I don't think you need the lines, like the edges of the surface, you don't have to, but if you want, we already talked how to cut it out, right? So depends on how you want to present your work, right? All right. If there's no further question, let's call it a day.